Hey grade 8s, we're going to try something different today. We're going to try a little bit of drawing. Not my strength, as you know very well, but we're going to do a little scientific drawing. Very simplified, oversimplified, and that's the way many scientific models have to be, just to illustrate a point. Today we're going to talk about subduction zones, and a subduction zone is where one type of plate, and you know that the crust, that thin layer around our planet that we're standing on right now, is divided up into sections called plates. They're moving around very slowly, like the speed of your fingernails, or 1 centimeter a year, or 2 centimeters a year. But there's no space between them, so they're either colliding and you get subduction or mountain building, or they're pulling apart so the mantle and magma from the mantle can escape, or they're scraping past each other. And you can imagine this, like 50 kilometers of rock scraping past each other. It gets stuck and then it releases, and it all happens in a short period of time, and that's where you get earthquakes. So I'm really oversimplifying this because that's the easiest way to understand it. So we're going to talk about a subduction zone today, and that's important to us because we live in one. The ocean, which is very close to us, is immeasurably heavy, right? If you've ever lifted a 5-gallon pail of water or 20 liters of water, you know that it's really heavy. Well, think of the ocean. Thousands and thousands of kilometers, square kilometers, tens of thousands, hundreds of thousands of square kilometers, right? And 7 or 8 or 10 kilometers deep, right? All that water pushing down on the ocean plate. So what happens to the ocean plate is it gets compressed, right? And it's very dense. It's heavy and dense. And the continental plates, you know, there's mountains and there's us and cities on top of it, but that doesn't equate to the same weight or pressure that all that water would. So continental plates are about 50 kilometers thick. Ocean plates are more like 15 kilometers thick, and they're really dense. So when they collide, and it happens very slowly, it's not like they're running at each other, very, very slowly, but it's a immeasurable amount of weight and pressure. So this is the ocean plate, this is the continental plate, much thicker. The ocean plate, the denser one, gets pushed down, and the continental plate kind of rides up over top of us. And this process of the ocean plate going down is called subduction. Okay, now there's no room down here, it's getting pushed down into the mantle. There's no room at all, so it creates so much friction. And we know that by rubbing our hands together, you know, that's a little bit of friction. This is a gazillion times more than that, right? So you get melting on it's called the leading edge of this oceanic plate down here. And as it melts, it expands, and there's already no room for it to be down there. So it finds its way to the surface and erupts. Now I'm gonna back up a little bit and walk you through this. So here we have a diagram. This is an ocean plate. So you can see this blue here is the ocean. This is an ocean plate all along here, okay? And it's being pushed down. But I have to back up for a little bit. Why is this ocean plate even getting moved around? Well, scientists believe, and there's a video that I'll get you to watch today before you start drawing this. Scientists believe that there's convection currents in the mantle. And a convection current works like when you boil a pot of spaghetti or a pot of rice, you get this circular boil, right? The hottest place is right at the bottom of the pan, right by the heat source. The coldest place is the air, because the air is only like 20 degrees, and where it's boiling it might be 100 or more degrees. So it rises away from the heat, and then it cools and sinks. So you get these circular boils. Well, the same thing happens much slower, obviously, in the mantle. So this is maybe 50 kilometers, this is 15 kilometers. Remember, the mantle is like, I don't know, what do we say, 2,200 kilometers, 2,600? There's different estimates. But you get this rising, because below the mantle there's the outer core and then the inner core, and that's the hottest part of our planet, maybe 10,000 degrees Celsius. It's just really warm, maybe 15,000 degrees, right? So you've got this magma, this kind of gooey, Play-Doh-y type magma. You've seen magma on TV before, rising until it hits the crust and it starts to cool, but there's no room for it to go because this is very dense, and it's 15 kilometers of rock. So it gets deflected, you know, left and right. Okay, and as it does, it also cools down. So it starts to sink back down again. Okay, and as it sinks back down again, it gets closer to the core, and it warms, and it starts to rise up again. Okay, and this happens in these, what scientists believe and call convection currents. So you get this process. Now, as this this magma is forced this direction, it starts to pull on the plate this way. And as the magma is forced in this direction, it also pulls on the plate this way. Plus, it's pushing up right here on the plate. And this doesn't happen overnight. This is thousands and thousands of years, hundreds of thousands, maybe millions of years, depending on who you talk to in time frame. Eventually, this is going to fail. It's going to break, okay? This is going to break right here, okay? And this plate's going to move this direction, and you're going to get an eruption on the sea floor, okay? And then the eruption, as it hits the cold water, will eventually cool down as this pressure, balances itself out, and you'll get this almost like a plug. And then the pressure continues, this process continues until it breaks again, and then you get another eruption. But as these eruptions occur, again, maybe over thousands, hundreds of thousands, tens of thousands, millions of years, right? This plate is moving this direction, and this plate is moving this direction. So this little mountain is going to get moved this way, and this little mountain is going to get moved this way. And there's lots of evidence to support this, but probably one of the most key parts of evidence is in the middle of the Atlantic, there's this rift, and they can see with sonar this exact phenomenon. You can see that right above where the rift would be, there's like mountains, there's ridges, and then there's a crack in the ridges, and as you move away from it, they get smaller and smaller because the weight of the ocean is compressing these, right? It's pushing them down into the ocean crust. Okay, so that's the process that drives this. It's called convection currents. And I wish we were all here together. Maybe we will all be, well, not all of us, but maybe some of us will be together next week and we can talk more about this. But the plates move this direction. So this plate's going to move, right? And remember, this is three-dimensional. These plates are out this way. So it's going to be scraping up along the plate here. It's pulling away from here, and it's converging here. So diverging here, it's converging here, it's converging over here, and there's transform boundaries on all sides of this. But the part we're going to focus on is right here. So as this plate, if we could go back in time, where this plate met the continental plate, as it meets, right, this is thicker and less dense, this is thinner and more dense. This gets pushed down into the mantle. Now there's no space down there. It's not like there's big caverns, right? The weight of the world is literally pushing down here. So this causes tremendous friction, tremendous pressure, and it starts to melt. But it also causes all kinds of cracks, because if you've ever tried to bend a rock, it doesn't work, right? So you've got fissures and cracks and breaks, right? So there's lots of breaks and cracks. And you get this whole zone right here, this subduction zone, where you're going to get melting and lots of pressure, like immeasurable pressure, right? And this melted lava, melted magma down here, it's lava up here, magma down here, finds its way through these cracks and fissures to the surface, where it erupts in what we know as a volcano, right? Like Mount Baker is a subduction zone volcano. Mount St. Helens was a subduction zone volcano. This process is like, this is where we live, this is the ocean beside us, and these are the volcanoes that form because of that. That's very simplified, but that's the process that happens. Now what I want you to do is I want you to try drawing this. Now you can look online, there's tons of diagrams of subduction zones, if you just Google it and hit images. But I want you to draw a subduction zone diagram, and you can color it any way you want, but be appropriate. You know, blue is a good color for the ocean. Maybe the mantle is kind of orange. Maybe these are grayish brown, the continental plate and the ocean plate. But you need these features. You need to label the ocean plate, the continental plate. You need to have convection currents. You need to have the mantle, right? This is called an ocean rift. This one right here. That's where it's breaking. This is a rift, R-I-F-T. This is called an ocean ridge. That's where the mountains are forming at the bottom of the ocean, okay? And then part of the subduction process that's very important to us, because we live on the surface, is as this process repeats itself over, again, a very long period of time, the magma makes its way to the surface, and over time, a volcano forms, okay? All right, so your assignment is this. You are going to draw me a picture of a subduction zone diagram, right? Just on a white piece of paper. Try to keep it, as realistic as you can, as realistic as we know. Take a picture of it, or better yet, if you have an iPhone or iPad, scan it. You go into Notes and hit the camera and use the scan function, and then send it to me at learn34.com. So give it a try. I want to see what you guys think of this. You can certainly just go online and Google this image and kind of draw from there as well. My drawing is not fantastic. This is a really quick and kind of dirty drawing. It's not very neat and clean. But do your best, give it a try. And we can always redo it. And I'd just like to see how you could do this one. Okay? Take care. We'll talk to you soon.